So really, here's what I would say about this whole thing in general with a pen. There's a theorem which I don't think you're required to know, but I'm going to tell it to you anyway. That basically says the following. So if the Taylor series for f of x has a radius of convergence equal to, say, r, and r could be 0 or a regular finite number or infinity, right? Those are all possible values for the radius of convergence. Here's what the theorem says. This is the theorem. Then so does the derivative of f of x, and so does the integral of f of x. So for example, it's a good example. Here's maybe our favorite, my favorite at least, function that's easily written as a Taylor series, 1 over 1 minus x. That function, the Taylor series, is equal to 1 plus x squared plus x cubed, right? It's just the usual sum from n equals 0 to infinity of x to the n. And we know for this series that the interval of convergence is everything between -1 and 1, right? Because your ratio has to be less than 1 in absolute value. And our radius of convergence is equal to 1. But here's what's really neat. If I take the derivative of this, f prime of x, so let's see, 1 over 1 minus x, that's really 1 minus x to the -1, whose derivative is -1 times 1 minus x to the -2 times the derivative of the inside, which is -1. So this is really equal to 1 times 1 minus x to the -2, or 1 over 1 minus x quantity squared. But here's the cool thing. If I take the derivative of this function, I can also take the derivative of the entire series here. Watch. The derivative here is, well, the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the 4th is 4x cubed. So on and so on and so on. And we get this derivative here is the sum of, we'll just take the derivative of x to the n times x to the n minus 1. And it's totally valid. And now here's where things get a tiny bit dicey. The radius of convergence is the same. So here, the radius of convergence is equal to 1. And just like in the previous one, the center is still 0. Here's where the diciness comes into play. And this is where the ratio test is kind of a big deal. The endpoints are a question. We don't actually know for this new series if it converges or diverges at 1 and or -1. And the thing is, we don't really learn in this class how to test the endpoints. There's definitely a way to test them, but it's not something we really talk about. And I don't think we need to spend time talking about that. But the whole point is that this series essentially converges on the same interval, plus or minus the endpoints. So maybe this series converges when x equals 1. It doesn't, right? If x is equal to 1, then you would have the sum of n. And if n goes from 0 to infinity, 1 plus 2 plus 3 plus 4 plus 5 doesn't converge, right? That definitely diverges. It fails the nth term test. So here we can just see, because we know things, that the interval of convergence is also -1 to 1. But it's totally possible for some other weird series that the interval of convergence could be -1 to 1, including the endpoints. So that's kind of the idea here, is that you can take any function Taylor series, differentiate both the actual function and the series it's equal to, and get a valid result. And the interval of convergence remains the same. Or sorry, the radius remains the same. The interval might be slightly different. Yeah, Josh.
Well, since we don't know that, like extra stuff,
Right.
in this class, would that interval of convergence be the same?
We never know for sure it's the same. It could, so I know for sure it's because we can show by the nth term test that this diverges if x is equal to 1 or -1. But for example, it could, for some other series, it could have converged at either endpoint. And we'll do a couple more examples just so we can. Also, I want to point out, if I was writing the series, I'm going to actually change where I start, not because it actually changes, but if I start at n equals 0, 0 times x to the 0 minus 1 is just 0. So I don't need to write that term. So I'm going to start at n equals 1 to infinity. Right? I don't need to get that term because when you add 0 to something, it doesn't change anything. Okay, we'll look at two more examples like this because it does show you something. So in fact, we'll even look at one example we did the other day, but from a different perspective. So I think last class, maybe the class before, we found the Taylor series for the natural log of x centered. Ooh, that's a good question, James. At x equal to 1. And it's honestly one that I never remember. I know it's in the textbook somewhere. We could, but instead of deriving it the way we did before, where we took all we actually used Taylor's formula, here's another way of deriving the Taylor polynomial centered at x equals 1 for natural log of x. X equals 1, a equals 1, who cares what we call it? We mean the same thing. So take the derivative of the natural log of x. That's equal to 1 over x. No, actually, that's a d. I know it might look like a. Yeah, was this way? Is this the way I really want to do it? Yeah, and then we're going to rewrite this in a way tricky. I would really love to write this as 1 over 1 minus something. Because I know if it's 1 over 1 minus something, then it's geometric. Right? The something is my ratio. So what does that something need to be so that 1 minus it is equal to x? Well, what? Not quite, because then I'll have 1 plus x on the bottom, and I just want x. So what I just need to do a little algebra here. I need x equal to 1 minus my parentheses here. So add my parentheses to both sides and subtract x from both sides. So I need 1 minus x in those parentheses. And that works, right? Because 1 minus x, the ones will cancel and you get a positive x. But look, now this looks like a 1 over 1 minus r ratio. And that's geometric. First term is 1, ratio is r. So this is going to end up equaling 1 plus 1 minus x plus 1 minus x squared plus 1 minus x cubed, and so on and so on and so on. And that's going to be the sum from n equals 0 to infinity of 1 minus x to the n. Now I'm going to write this just slightly differently to make it a little bit easier to deal with. Usually when we write a power series, we really want to have x minus the center, not the center minus x. So I'm just going to do a tiny bit of algebra to make it look nicer. So here's the little bit of algebra. I'm going to rewrite 1 minus x to the n as -1 times x minus 1. That work? Is that valid? Let's see, -1 times x is -x. Yeah, -1 times -1 is +1. That should be valid. And then when you have a product raised to the nth power, you can just write each part to the nth power. This is really equal to the sum from n equals 0 to infinity of -1 to the n times x minus 1 to the n. So another way of writing this, if you prefer, would be to write it as 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed, and so on and so on and so on. These two things are the same, they just look a little different. But they really are the same. Is 1 minus x squared the same as x minus 1 squared? It is. You don't even have to factor out a negative. What's x minus 1 squared? Okay, what's 1 minus x squared? 1 minus 2x plus x squared will look the same. The thing that's happening here is it doesn't matter what x is, right? If x is 5, 5 minus 1 squared is still the same as 1 minus 5 squared. Whether the insides are positive or negative, as long as they're the opposite values of each other, when you square it, doesn't matter anymore. So all the even power terms work out just fine. All the odd power terms have opposite signs. So here's the gist. I took the derivative of the natural log to get this. So this whole thing here is the derivative of the natural log. Well, I want actually natural log, so I'm going to anti-differentiate both sides. So if the derivative of the natural log of x is equal to the sum from n equals 0 to infinity of -1 to the n times x minus 1 to the nth power, then we can, before I do that though, give me 1 second, sorry, I just want to pause 1 sec. I should talk about the interval of convergence really quickly. So this geometric series, right, it's still geometric, even though it's a power series. This geometric series definitely converges when the absolute value of our ratio is less than 1. Or in other words, when x minus 1 is between 1 and -1, if I add 1 to each side, when x is between 0 and 2. Which makes perfect sense, right? The interval is still, or the radius is still 1. The interval is from 0 to 2, exclusive of either endpoint. Right? You can't plug in 2, you can't plug in 0. Won't get, especially 0, right? Natural log of 0 is like that. But if you plug in 2, it won't work either. Because you get 1 plus -1 plus 1 plus -1 plus 1, which just doesn't converge. Okay, but now we're going to say is if the derivative of this function equals this other thing, then I can say that the natural log of x equals the integral of this series. Which I know is kind of funky to write, but it is. Now, it might look terrible, but it's actually not. Because when you integrate this, all you really have to do is focus on the fact that you've got x. So what's the antiderivative of x minus 1 to the nth power? Well, that's not bad at all. It's going to be just x minus 1, the n plus 1 divided by n plus 1. And technically, when you do an indefinite integral, like if I said, I know it's going back to me. If I said what's the antiderivative of x squared, what would you all tell me it is?
Plus c.
Right, plus c. Technically, we need a plus c here. But it's not, but we can find c by figuring out what's happening at the center. So if you plug in 1 for x, what do you get on the left side? Right, and that is often the case. If you plug in 1 on the right side, well, when you plug in 1 for x, you get 0, plus 0, plus 0, plus 0, plus 0. So you get a bunch of zeros plus c. So c has to be 0. The point of finding c is so that we actually get the what natural log of x is equal to as a function. Because maybe it's going to turn out to be something, it is most of the time 0, but it is not always 0. Although the real answer is you're probably not going to actually be doing this process, so you shouldn't worry. Yeah.
In class, what he did was he changed the variable of x to t, and he made it with respect to like dt.
Right. Sure. Yeah. He did like he used the fundamental theorem of calculus.
Yeah.
That's also a totally fine way of doing it. It's essentially the same work, just written a different way.
Okay.
So here's what we've got. We've got that the natural log of x is equal to the sum from n equals 0 to infinity of -1 to the n times x minus 1 to the n plus 1 over n plus 1. And now here are things that we know. We know that the radius of convergence is still 1. But the interval of convergence, we don't actually know what's happening at 0 or at 2. And we don't have the tools to say what is happening at 0 or 2. Let me point out. Sure, let me point out. So here's my series again. And if we look at the endpoints, x equal to, let's start with 2. Well, if I plug in 2, is 2 where I want to start? Yeah, that's fine. Interesting. Really? So I'm just, no, my brain, I'm just thinking first. Oh, I forgot the n here. Okay, cool. So what we're doing here, so here's what we're saying. Let me back up, because I feel like we would like to see the context here. So we know that this series converges when x is between 0 and 2. Well, maybe we don't actually really know that. We know the previous one does, right? For sure, this converges with x between 0 and 2 because it's geometric, and the ratio is between 0 and 1. Or the ratio is less than 1 in absolute value, right? That's given. And then I said there's this theorem where if you take a derivative or an antiderivative of your series, the radius doesn't change. But why would you believe? I mean, you believe me because I'm a nice guy, I'm trustworthy, I would not lie to you. But here's why this actually works. I can use the ratio test here. If I use the ratio test, look what happens. Limit as n goes to infinity of my an plus 1, okay, -1 to the n plus 1, x minus 1 to the n plus 1 plus 1 over n plus 1 plus 1 times the reciprocal, plus 1, -1 to the n times x minus 1 to the n plus 1. Putting like things together, if the limit as n goes to infinity of, okay, we don't really care about the -1s because they're just going to go away. X minus 1 to the n plus 2, or x minus 1 to the n plus 1, that's just going to be x minus 1. And finally, n plus 1 over n plus 2, that's the part we're actually going to take the limit of and get 1 for that part. So here's what we get. We get the limit, then goes to infinity of the absolute value of, just make that go away. You get x minus 1 times n plus 1 over n plus 2. And that limit is 1. So you just get the absolute value of x minus 1, which is less than, well, we need to be less than what? Yeah, right, ratio test. If we want convergence, then the limit of the ratio has to be less than 1. And if we want divergence, the limit of the ratio has to be greater than 1. But if the limit is equal to 1, what does the ratio test tell you? Right, and that's the thing. If x is equal to 2, if x equals 2, the ratio test is inconclusive. Because 2 minus 1 is 1. And if x equals 0, the ratio test is inconclusive. Because 0 minus 1 in absolute value is still 1. So that's what we mean by testing the endpoints. It's because when you test the endpoints, the ratio, you're testing them because the ratio test doesn't tell you anything about them.
Where did you get that?
Oh, well, I got that. I just didn't finish solving this inequalities. Right? It's x minus 1 between 1 and -1. At 1, you get 0. But here's what I want you all to see, though. Right? The ratio test produces the same interval as it would have for the previous series, which is always the case when you take derivatives or antiderivatives like this. Now, again, I don't think you're really going to be doing this, which is why I don't want to focus too much on it. But he did talk about it in class, so I feel like it bears some explaining. So just to kind of wrap this part up. If you plugged in, actually, let's start at x equals 0. So if we wanted to test the endpoints here, if I plug in 0 for x, I'm left with the sum from n equals 0 to infinity, -1 to the n times 0 minus 1 to the n plus 1 over n plus 1. Okay, let's simplify that a little bit. -1 to the n times -1 to the n plus 1. What's that always going to equal? Let me ask you a different question. If n is even, what's -1 to the n going to be? If positive 1, right? If n is even still, what's -1 to the n plus 1? Right, it's an odd power, and -1 to an odd power is specifically negative what? Right, -1 to an odd power is always -1. So if n is even, then we're going to get -1 over n plus 1. Okay, before we go on, what if n is odd? What's -1 to an odd number? What's -1 to an odd number plus 1? So you still have -1 times positive 1. It's still -1. So actually, for any n value, whether it's odd or even, you're always going to get this. But this looks like this, and this, although not exact. Well, actually, no. This exactly is a p series. If I start times -1, this is -1 times n equals 0, I get 1. N equals 1, I get 1/2 plus 1/3. That's exactly the harmonic series, and that series diverges. So x equals 0 is not included in the interval of convergence. Yes. Yeah. Because I could, now I know this doesn't look exactly like a p series because usually it has to be 1 over n to the p, but I could rewrite this. I can rewrite this as the sum from n equals 1 to infinity of 1 over n. They're literally the same. It's just one is written in the format that we actually recognize looks like a p series, and the other one is slightly off of that. But I re-indexed, right? Starting at 0 gets me 1 over 1. And then plugging in 1 gets me 1 over 1 plus 1, which is 1 over 2. And then 1 over 3. And then 1 over 4. It's the literal actual same series, which we know is divergent. And the -1 times the divergent thing is still a divergent thing.
Would you recommend doing it this way or
Which other way? Oh, like when we use Taylor's formula, I would probably I probably wouldn't do this at all unless you specifically wanted you to, but I don't think you actually want to. It's not something that's usually in the curriculum of this course. I just felt like since you said it in class, I should offer more explanation. Now here's what I'll point out. If we test the other endpoint, right, where again this series, we don't know if it converges or diverges at x equals 2 because x equals 2 makes the ratio test limit equal to 1. And that's inconclusive. So if we plug in 2, look what happens. We get the sum from n equals 0 to infinity of -1 to the n times 2 minus 1 to the n plus 1 for n plus 1. And that's equal to the sum from n equals 0 to infinity of -1 to the n times 1 to any power is just 1 for n plus 1. And now here's what I'm going to tell you without proof. This series is a convergent alternating series. And it converges by something called the alternating series test, which we do not learn in this course. But it does converge. And so I'll just point out that this series, f of x, this series for natural log of x, which is the sum from n equals 0 to infinity of -1 to the n times x minus 1 to the n plus 1 over n plus 1. The interval of convergence is actually 0 exclusive, which makes a lot of sense because natural log of 0 is very undefined, to 2 inclusive. Again, I haven't justified that, but I've told you, and I know it is true, that this series does converge in that. So that's what I mean when I say the radius of convergence is the same no matter how many derivatives or antiderivatives you take. The interval of convergence might be slightly different at the endpoints because the other series, the one we took the antiderivative of, the sum of -1 to the n times x minus 1 to the n, the interval of convergence here was specifically open print 0 exclusive to 2 exclusive. It did not converge when x is equal to 2, whereas this series does converge. So not that important, but I didn't want you to be like, why is this? What I wanted you to know one. Something else I was going to say here. Maybe not. I had a thought. It went away. Sorry. Yeah.
I just had could you go like to the previous page?
Yes.
I was just like, why did we have to like change it from 1 minus x to n?
We didn't. But I chose to do that because we are more used to seeing the power series written as x minus your center raised to the nth power.
Oh,
It's just more standard way of writing. And remember the other thing I wanted to say, which is that you could write this series like this at the very end, but I will tell you, people will often re-index it so that you start at n equals 1. So it would be just as valid to say, how do I want to do this? Here's kind of the process that people actually use. I'm going to say, I'm going to use m for just a second. Let's say that m is equal to n plus 1. So then if n starts at 0, where is m going to start at? Right? It's not a trick question. So we're going to start at m equals 1 to infinity. And then I'm going to have negative 1 to the, well, n is equal to m minus 1. So I have negative 1 to the m minus 1. And then I have x minus 1 to the m over m. And so then people go back and say, but I want to use n instead of m. So I'm going to change all my m's back to n's. So they write it as the sum from n equals 1 to infinity of negative 1 to the n minus 1 times x minus 1 to the n over n. I don't exactly know why you would really care about doing that, but people seem to really care about doing that sometimes, so they do. Question?
So, you know, solve like a value. So you know how like for this question you did, like it said like use the Taylor series to find the natural log and set it at x is equal to 1. What like you know how we're supposed to set out for Taylor series? When do we know?
Well, so when someone asks you to find a Taylor series, you have to ask yourself which way you're going to go. Meaning, are you going to go formula, take 5 derivatives, plug in your center, and try and find a formula, or you're going to go using things I already know. Meaning, for example, someone said, find the Taylor series centered at x equal to 0 for f of x equal to, sure, sine of x divided by x. Centered at 0? Centered at 0 might be a poor choice here, James. Right, because if you plug in 0, it's kind of like but that's I don't like that problem. Sure, 0, fine, whatever. So the point is, you could start by taking derivatives. This problem might not actually be really valid, but it's fine for my purposes here. So you could say, okay, well, oh man, it's gonna be trouble from the start, right? F prime of x is x times cosine minus, yeah, it's going to be the center is 0. No, okay, yeah, this is center 0 is wrong. Fine, okay. Let's make it. I was trying to do something cool, but we'll make it not cool. Let's say it's f of x equal to x times sine of x, which can totally be centered at 0 because then you can actually evaluate it at 0. If you start taking derivatives, things start to suck pretty fast. First derivative is 1 times sine plus x times cosine. Second derivative is going to be cosine plus 1 times cosine plus x times sine. And maybe this one doesn't actually get too terrible because you can kind of combine things together, but things start to get gross. Or you can use knowledge we already have. We know, or we should memorize, that sine of x is equal to all the odd powers of x divided by that same number factorial, and the terms alternate. So it is x to the first over 1 factorial minus x to the third over 3 factorial plus x to the fifth over 5 factorial. And it just continues on and on and on. You definitely should memorize this one. And you can write it like this if you want to. It's the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. And then multiply the whole thing by x. So x times sine of x, all those powers of x are just going to increase by 1. You're going to get x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial minus x to the 8th over 7 factorial. And we can even just multiply the formula as well and get negative 1 to the n times x to the 2n plus 2 all over 2n plus 1 factorial. And it's definitely the way most people intend for you to do a problem like this. So if you see a function that you're asked to find the Taylor or Maclaurin series for, and it's a known thing modified a little bit, like e to the x or sine of x or cosine of x or 1 over 1 minus x, those four things you'd be like, oh, I know what those are, and I can manipulate them. All right, I think that's kind of the answer to the question you're asking. However, there are things that, and then there are things like this, like the natural log thing, or like the arctangent of x thing. So if someone said to find the Maclaurin series, which is just the Taylor series centered at 0, using a different word because it exists, for f of x equal to the arctangent of x centered at 0. It might, no, I feel like it's still stupid and gross to try and do it the long way. But so here's what I should really say. I don't think this could really be a question on your exam, unless he really expects you to be differentiating and anti-differentiating series. I don't imagine that's what he's actually saying he wants you to do, because it's not part of the syllabus or the curriculum course. But he did show you this example in class. So one way. Oh, so here's maybe a plausible question. We'll start with the following. Find the first 3 non-zero terms. This might be plausible doing it the long way. It might still absolutely suck. So let's see. So f of x is arctangent. F of 0 is, what's the arctangent of 0? Let me ask a better question. What's the arctangent of 1? Or in other words, what is the angle that if I took tangent of it, I would get 1? Yeah, exactly. Right? You're looking for the angle. If you take tangent of the angle, you get the value you're talking about. So arctangent of 1 is pi over 4. Arctangent of 0 is 0 because tangent of 0 is 0. Now I feel like that one feels kind of like just like whatever. So I think the pi over 4 example is better. Great. So then my first derivative here is 1 over 1 plus x squared, which I never did we talk about arctangent derivatives before? No. Did you talk about this in class? You must have a little bit. Right. Right. And there's a whole story behind this, but for another day, meaning not in this class. Great. So I'm going to get a non-zero term there. But now if I take the next derivative is going to be, okay, got to use the quotient rule. Let's be a little bit smarter about this. Let's write this as 1 plus x squared to the negative 1. So the derivative is negative 1 times 1 plus x squared to the negative 2 times 2x. Which is negative 2x over 1 plus x squared. And when I plug in 0 there, I'm sad, as f double prime of 0 is 0. So then we go to the third derivative. Okay. No, we shouldn't do this, right? It's stupid. It's terrible. So the point is, although technically possible, if you really have, like, if you have a computer, you can brute force this and just keep finding all the derivatives and plug in 0 and eventually get the terms. But the way we usually, if we can, try to find series for a function is we try and make it look like something we know. We try and make it look like e to the x or sine of x or cosine of x or 1 over 1 minus something. And that's what we're going to do here. We're going to say, well, our tangent doesn't look like 1 over 1 minus something, but its derivative. The derivative of the arctangent of x is 1 over 1 plus x squared, or as I'm going to write it, 1 over 1 minus some stuff. Negative x squared. And hey, this looks like what a geometric series adds up to, where that's our ratio. And that's our first term. This is literally equal to 1 plus negative x squared plus negative x squared squared plus negative x squared cubed Or you can write it as 1 minus x squared plus x to the fourth minus x to the sixth and so on. And that's just going to be the sum from n equals 0 to infinity of negative x squared to the nth power. Which if we're trying to make, sorry, that looks a little bit terrible. Yeah, let me zoom in a little bit. And then we should rewrite this as the sum from n equals 0 to infinity of negative 1 to the nth power times x squared to the n, or x to the 2n. Yeah. Like, why am I writing it like this and not like this? Because I know that when I have a geometric series, 1 plus my next term, which is just the previous term times the ratio, plus the next term, which is my previous term times the ratio. If I keep just multiplying by the ratio, that always adds up to, if the ratio is between 1 and negative 1, it adds up to 1, or the first term, over 1 minus the ratio. So I'm kind of starting with this and working backwards to that. Oh, sorry. Yeah, sorry. I'm starting with this and working backwards to that. So I'm always trying to get 1 over 1 minus a thing. That's why I took 1 over 1 plus x squared, and we wrote it as 1 over 1 minus x squared. Right. If you see 1 over something with an x in it, you want it to look like 1 over 1 minus some stuff. And then whatever the stuff is, that's your ratio. Okay, but now, well, that's what the derivative of the arctangent is equal to. So if I want to find the actual arctangent of x, I'm going to say, well, arctangent of x is equal to the antiderivative of the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n. Or you can do the thing where you go from 0 to x and make it to the 2n. I guess I don't really want to. Not my jam. But then the only thing you have to worry about integrating is just the thing that has x. Everything else is a constant, so we get the sum n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1, 2n plus 1. It's kind of wild. And then there would be a plus c, but I'll tell you, just like before, the plus c ends up being 0. It's kind of a neat series. Like, the series for arctangent of x is interesting, but I don't know how much we need to talk to. Oh, one last thing before questions. So back here for a second, and I always forget to do this part. So this original, the series, this series here, 1 over 1 minus negative x squared, this series has an interval of convergence where our ratio, which is negative x squared, is between negative 1 and 1, which just ends up meaning that x has to be between negative 1 and 1. So that gives us that x is between 1 and negative 1. Our radius is equal to 1. And similarly, the radius here is also equal to 1. But this one definitely converges at one of the endpoints and diverges.
So if we showed that work instead of getting, from the x to 0, we just showed that plus c and we put an arrow to say that goes to 0.
You actually, so you should really, if you're going to do it like this, what you would actually need to do is then say, plug in the center. So plug in a equals 0, and arctangent of 0 is 0, and it's equal to the sum from n equals 0 to infinity of negative 1 to the n times 0 to the 2n plus 1 over 2n plus 1 plus c. But then this entire value here is 0 because you're just adding up 0 every time. And whatever this value here is equal to, that's your c value. It just happens to be 0 in this case. But sometimes you can be centered somewhere where this actually ends up not being 0. Yeah.
I was just gonna ask, are we integrating the series to find the plus the c, or like?
We're integrating the series to get the new series. But when you integrate a function, you get a plus c, right? It's an indefinite interval. And so there's a plus the constant at the end.
Like other scenario would be to like integrate the.
So here's the thing I'm gonna say. I don't think you ever are gonna have to do this. I don't think that's my best guess of his intentions, is that you don't, he was showing you a thing because he wanted to. I don't exactly know why, but and so maybe you should ask for clarity from him, because this topic certainly isn't in the syllabus. Yeah, definitely not. But that doesn't mean right. It wouldn't be the first time a teacher had asked a question about something that wasn't in the syllabus. So I would certainly ask for clarity about it. You know, like, could this appear on the final? Do we have to be able to take derivatives and antiderivatives of series? It's not something that's in the syllabus, but just because there's not a lot of examples where you actually do this. These are kind like the two we've seen today are kind of the two prime ones. Like, actually, so here's a question that if I were a teacher and wanted to throw something crazy, maybe this could be an extra credit question. But you could do it the short way. Maybe not extra credit, but you could say, like, I want you to find the series for f of x equal to the natural log of x plus 1 centered at x equal to 0. And you could do this the long way, or not the long way. I mean, well, you could do it either the Taylor's formula way, right? Take all the derivatives, f of prime of x, f double prime of x, and so on, plug in the centers, and so on, get some values, find the formula. Or you could do this one the way we did the other natural log one, by taking the derivative. F prime of x is 1 over x plus 1, which is 1 over 1 minus x, and do it that way. I could see that that's like not a bad question, because it's also fairly easy to get to see the geometric kind of thing. I could see him, if he really was dead set on asking you to do this sort of thing, giving you this function and saying to do it that way by differentiating it and then finding the series. But there's not a lot of other great examples of things like this. Yeah, just. I would recommend doing it the way you are more comfortable with. That's the real answer, which is probably the formula way. You shouldn't have that much time. Honestly, like you should not. I would say no, you shouldn't do it that way.
Real quick, when it comes to the radius of convergence, I kind of just remember that as like the equation of like, not saying that's, it's exactly c, but x minus c,
Right.
value less than,
Right, exactly.
less than 1.
Right.
And then what you do is you get that to be equal to that. So let's say you have an equation like x minus 2 absolute value over 2 is less than 1. You put that 2 over. So then I just always just write r equals 2.
Right. That's very legit.
Okay.
Right. So basically, once you've done your ratio test, if you get to a place where you've gotten ratio test, and you get to a place where you've got like the absolute value of x minus your center over some value, let's say. No, I was gonna make up something more general. Actually, I didn't want to use n. I was trying to pick a letter that was like x minus a over z, where z is just some number less than 1. Z is your radius, because you're rewriting this as the absolute value of x minus a less than z.
So you don't have to do the whole like solving for both.
Right. And the thing is, in this class, we're not usually asking about the interval of convergence because we don't have ways of testing the endpoints. We haven't talked about it. So that's your radius. Basically, you have to get to a place where you have x with a coefficient of 1 minus whatever the center is, like that. So yeah, for example, if you had the absolute value of x minus 2 over 3 less than 1, your radius is clearly 3. And you can see it that way, or you can do the other thing I've talked about in class before, which is saying, well, that means if you really wanted to, you can say that means x minus 2 is between 3 and -3. You definitely shouldn't do it this way. This is the more work way of doing it. And then add 2 to both sides. So you get -1 less than x less than 5. And then your diameter of convergence is 5 minus -1, which is 6. And so then your radius of convergence is half of that, which is 3.
Thank you.
You're welcome.
So the last part is like another way of.
This is the way I always like to think of it, because most of the time when I'm doing these things, I'm actually also having to find the interval of convergence. So it's really not like an extra piece of work to do. I just don't like having to, like, for example, if you had something like, if you ended up at a place where like your ratio test gave you like the absolute value of 16x plus 7 less than 1. It's kind of a pain in the butt to say what the radius is from that equation. It's not that hard. The radius here is definitely 1/16. But it's kind of annoying.
Don't you have to like say, okay, so in this case, we're converging, you have the absolute value, so you have 16x plus 7, which is less than 1, and you have 16x plus 7, which is greater than -1.
Right.
And then.
Right. But the real answer to what the radius is, if you've got this equation, is the radius of convergence is always the reciprocal of the coefficient of x. I should say the absolute value of the reciprocal of the coefficient of x. So if the coefficient of x is 1/3, which it is here, the radius is 3. The coefficient of x is 16, the radius of convergence is 1/16. If you end up with something stupid like the absolute value of -5x plus 2 less than 1, then my radius of convergence is, yes, exactly, 1/5. Yeah, just.
And then, so I guess when you're like, on with the -1 is less than x and less than 5,
Mhm.
when do we have to like, I guess, show that work? What is that like?
Yeah, I don't think you ever have to show this work. I just like showing it.
Actually, like, those questions are just asked.
Like, yeah, right. Once you get to here, you can stop and say the radius is 3. I like to do this because I don't know, that's the way I always done it. But yeah. And you should, and again, reiterate, we shouldn't be asking about interval because, or if we are, we shouldn't be asking about the endpoints because we don't have a way of testing the endpoints. Unless you have, I should say,